Decom Tools is EU-funded project which has two targets: saving costs and lowering CO2 footprint of decommissioning of offshore wind farms. One part of this project was also to demonstrate wind turbine blade recycling through pyrolysis process. There are different pyrolysis technologies available, but by default they have one aspect in common. The material is brought to high temperature without exposure to oxygen. Therefore, the material is not burned, but it does start reacting and transforming to gasified form when the temperature is high enough. All these gases are then collected and further cooled down to so-called pyrolysis oil, which is to some extent similar to crude oil. Some gases can also be collected separately. If some of the material doesn't react, it stays in the reactor and can be removed after the reactor has cooled down. In general, there are two inputs, material and heat, and three outputs, pyrolysis oil, gases, and residue.
So we received wind turbine blade pieces from TPI Composites, which we further processed in the NRP location through a batch pyrolysis process. These pieces that we received from TPI Composites were approximately 1 meter long and 30 centimeters wide. So relatively big pieces, considering that normally this type of testing is done in a laboratory scale.
In both batches, the pieces were randomly chosen and included both carbon fibers and glass fibers. With both batches of test material, temperature of 550 Celsius degrees was used, and the test material was exposed to this temperature for approximately 90 minutes. The cartridges were always emptied after the pyrolysis process from non-reactive glass and carbon fibers and other residue. The pyrolysis oil was recovered only once after both batches had been processed. The pyrolysis oil was further analyzed and processed by BioBTX in a laboratory scale to BTX, which is a combination of benzene, toluene, and xylene, one of the most used chemical compound and main building block of hundreds of applications in chemical industry. Some of the recovered fibers were further treated by TNO in high-temperature oven, which resulted to cleaner fibers with less contamination on them. Total of 79 kilograms of wind turbine blade pieces were tested, resulting to 16 liters of pyrolysis oil and 57 kilograms of fibers and residue. Considering that approximately 30% of the weight of the wind turbine blade is resin and 70% are fibers, the conversion is balanced. According to BioBTX, the pyrolysis oil consisted 10% of water, 10% of residue, 15% of alkylated phenols, and 60% so-called heavies. All phenols were converted to BTX. The thermal cracking of heavies has a potential to increase the yield of BTX. The division of these compounds in the pyrolysis oil can also differ depending on the blade type, section of the blade, and the processing conditions. The quality of the fibers were dramatically improved during the oven treatment of TNO, even though small residues could be observed in microscopic scale. No additional testing was done to the fibers, but it can be expected that the exposure to high temperatures has had an impact on the strength of the fibers. Processing wind turbine blades with pyrolysis is one of the potential solutions for old wind turbine blades. The approach requires optimization towards continuous process, which can be steered either towards maximizing the pyrolysis oil volume and quality to substitute crude oil in the chemical industry. This provides the opportunity to keep the carbon circulating in the products. However, the energy needed for heating must come from external sources. The second option is optimizing towards the fiber recovery. When the main market need is on the glass and carbon fiber side, it is possible to use the obtained pyrolysis oil for process heating. However, this releases carbon emissions. The most sustainable option would be to use the energy from renewable energy sources for the heating of the pyrolysis process and steer both the pyrolysis oil and fibers to new material manufacturing, therefore closing the loop of carbon as much as possible and substituting virgin raw materials.
We have a pyrolysis process with a batch process, and for us it's really interesting to get difficult waste streams back to an original base in the form of oil and gas. We were really interested in how the windmill blades will behave in our cartridges. So for the next testing is mass balance and energy balance the big goal.
Our technology, as mentioned, is able to convert end-of-life waste streams into a new high-value chemicals. And as we have done within this project, we have transformed the end-of-life wind blades into new chemicals. I think the biggest challenge with the wind blades was everything that all the inert materials present in a wind blade. So that you can think of the glass fibers and everything that is not easily broken down, and the inert materials, because inert materials do not convert into the chemicals.
We only performed the combustion, so we received black colored samples, and we expected that there was only glass fiber in it, but at the end it looked like some of the fibers didn't turn white, so it was carbon. So biggest lesson learned: material passport. We have to know exactly what type of material is in it before we use it as feedstock for our furnace processes. The market is really demanding about end-of-life solutions for their blades, so there's a big potential. And but the potential is there if the fibers have the right quality. And within TNO we have different research projects on this topic to maintain as much as possible the mechanical properties of the recovered fibers.
So the pilot that we did in this Decom Tools project was a very nice starting point, but there is still a lot of things to learn. We should optimize the process so that it can actually handle steady flow of material, and we need to think in which locations would these type of processes be needed, because obviously the decommissioning is a project-based approach, and often pyrolysis processes need a steady flow of material. There is a lot of opportunities of collaborating with other industries, such as with the marine industry, with boats, and this is also something that is looked into on different research projects, how to optimize the circular strategies for composite materials, and what are the best strategy for it, and in which locations, which type of strategies are the most efficient ones.